Swayam Prabha. Digital India. Educated India.
Today we will be talking about Jacobian and singularities. So, very briefly I will revise what was done in the last class. So, in the last class we were talking about inverse kinematics and forward kinematics, and we explained that inverse kinematics is essentially the relationship between the end effector position and coordinate and the joint angles. So, if you look at our hand, for example, if I look at my hand, then essentially the position orientation of the end effector, that is my hand here, is related to the joint variables. There are two thetas here, 2 thetas here and 3 thetas here. So, inverse kinematics basically gives us the relationship between the end effector position and orientation with respect to the thetas. So, what is required for our control system when we design our control system is, if I want to go from one point to another point in space, essentially I need to find the thetas at this point and then find the thetas at this point, the respective thetas of the joints, and then the controller is going to move the arm from here to here in some time t. Now, there could be, so what is important here is that when I am moving from here to here, how is the arm moving? So, each joint has a motor. In our hand it is the muscles. So, the muscles actuate, the joint moves and the end effector moves in space. In the case of the robot, there are at each joint there are motors, there are encoders, position feedback, and there is a gear for increasing the gear ratio, for increasing the torque at the joint. Now, in the case of the robot, what would happen is, when we are giving a voltage to the motor is going to move, the joint is going to rotate, and then the end effector is going to move, right. So, what we need is some relationship between the joint velocities at the joint and the end effector velocities. Why? Because at the end of the day we want to move the end effector in space in a specific trajectory with some velocity. So, today we will be looking at the Jacobian, which relates the end effector velocity with the joint velocities, and now this is essentially a mapping between the joint space and the end effector space. Now, there are points where the end effector cannot go, and such points are called singularities, and we have to ensure that when we are planning a path, the trajectory of the end effector does not go through a singularity. So, today's lecture essentially is on Jacobian and singularities, and let me explain by drawing a figure of a 2-link arm here. So, we have a 2-link manipulator, and at every joint of this manipulator there is going to be a motor, and there will be an encoder in front, encoder at the back, and there will be a gear in front, right. So, there is a gear to decrease the speed and increase the torque, and there is a motor. Now, how does the motor move? We give an input of to the motor in terms of voltage. So, when we give a particular voltage to the motor rotates, and when the motor rotates, the joint rotates. So, this is my variable theta 1 and this is my variable theta 2. So, when the motor rotates, this joint rotates, and when the joint rotates, the end effector position x y, in this case it is only 2D, is going to move either this side or it will move this side, right. So, that is how the so there is a mapping between the voltage which is being given to the motor to the joint velocity there, which is theta dot, let us say theta 1 dot and theta 2 dot, and the resultant end effector velocity, which is x dot and y dot. Okay. So, what we need to do from the controller point of view is to find a relation between the motor, the joint velocities and the end effector velocities, and also this mapping is very important because is it a 1:1 mapping, is it a many:1 mapping? Are there cases where we can give a joint velocity and the end effector does not go anywhere? For example, this example is if I have my arm like this, at this point the position orientation of my arm is fixed. So, if I give a joint velocity here, if I give a series of joint velocities, you can see that the end effector, the joints are moving, but the end effector is not moving. So, it also means that there is a possibility that if I give some kind of velocity on my onto my joint, then it has no effect on the end effector. So, this mapping between the joint velocities and the end effector velocities is very, very important, and points where it cannot go to are called singular points, and we need to find them out. So, let us see further today. So, what I am talking about is we are giving an input which is my voltage. So, we can call this the voltage space. So, this is in volts, and the input from the voltage space will take it to the joints. The joint is going to rotate. So, this is my theta dot, which is in degrees or radians, degrees per second or radians per second. And when the joint rotates, it goes to the end effector space, which is Cartesian space, which gives a resultant of x dot and y dot, which is the end effector velocity. Now, I want to know that if I give some joint velocity here, it goes to a particular output that side. Now, is it a 1:1 mapping, is it a 2:1 mapping, or what can, or does it go into somewhere else where there is no output? So, essentially I am giving some input which I just showed, and then the end effector does not go anywhere. So, where did the velocity go, right? And there would also be cases where which are not possible. So, this mapping to go from here to here, from this space to that space and that space to that space, is it can you go in the forward direction, and can you also go in the backward direction? By backward I mean, for a desired end effector velocity, can I get a corresponding joint velocity? Is that always possible? Are there cases where it is not possible? So, let us look further into how do we derive the equations. And for a two-link manipulator, it is easy to understand. So, let us do it for the two-link manipulator first. So, this is my two-link manipulator, and this is my x axis, and that is my y axis. And this is theta 1, this is theta 2. The link lengths are L1 and L2, and the end effector position coordinate, that is x and y. Now, what I want to do is I want to find a relationship between the joint velocities and the end effector velocities. Now, in order to do that, what I need to find is a relationship between the joint position and the end effector position. So, I am going to write it x is in terms of L1 cos theta 1 plus L2 cos theta 1 2. So, you can see that, well, if I draw it a little bit here. So, this is my xy, and this is theta 2. So, essentially when I am saying x 1 is equal to L1 cos theta 1. So, this is my x 1, and this is my x, and that is my y, right, in terms of coordinates. So, essentially x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and y is equal to L1 sin 1 plus L2 sin 1 2, right. Now, this gives us the relationship in terms of the position, the end effector position with respect to the joint angles. L1, L2 are link lengths, and they are fixed. Now, if I want to find the velocity, then what I can do is I can take the derivative of the left hand side and the derivative of the right hand side. Now, on the right hand side, what we have are two variables, theta 1 and theta 2, right. There are two variables, theta 1 and theta 2. So, if I want to take the derivative here, first I differentiate with respect to theta 1, then I differentiate with respect to theta 2. Okay. So, I can write it in this form, dx is equal to, first I am going to take the derivative with respect to theta 1. So, cos theta 1. So, I am going to get minus L1 sin theta 1 minus L2 sin 1 2. So, this has theta 1 and this has also theta 1. So, I get this and this. Then I take the derivative with respect to theta 2. So, there is no theta 2 here. So, it is 0. There is only theta 2 here. So, I get minus L2 sin 1 2. And in the next case, what we do get, so let me write it in matrix form. It becomes clearer here. So, I am writing it like this. So, this is d theta 1, this is d theta 2. And in the second case, we differentiate this dy, and what we get here is in terms of theta 1 first. So, I get L1 cos 1 plus L2 cos 1 2, and in the second case I get L2 cos 1 2. Okay. So, in matrix form, we get the relationship between the end effector velocity, which is dx, and the joint velocity is d theta 1 d theta 2, and this matrix is what we mean by the Jacobian matrix. So, the Jacobian matrix relates the end effector position, relates the end effector velocity with that of the joint velocities. And we should remember something here is that when I say velocity, I do not mean average velocity in meters. What I mean is incremental velocity. So, this dx, d theta are incremental. So, it is basically incremental joint velocity with the incremental end effector velocity. Okay. It is not the average velocity. So, now what we see here, we can write it in the form x dot is equal to j into theta dot. Okay. And where j in this case is a square matrix, it is a 2 by 2 matrix, okay, and it is square. So, there is a square matrix. In the case of a redundant manipulator, for example, if I add one more link here, suppose I add one link here, then it will become a non-square matrix. So, let us not worry about that now, but just to know that that is also there. In this case, it is a square matrix, 2 by 2 square matrix. Now, what is important here from the control point of view is, for a desired end effector velocity, I need to know what is the joint velocity. And how do we get that? We get basically theta dot is equal to j inverse of x dot. Okay. So, this gives us the relationship between the joint velocities and the end effector velocity. And further, if you look at this, then this becomes equal to theta dot is equal to adjoint of j divided by the determinant of j into the end effector velocity x dot. Okay. So, this tells us that to get a particular joint end effector velocity, we need to multiply it with the inverse of the Jacobian, and that is going to give us the joint velocities. Now, if you look a little bit in detail into this equation, what we do see is that the determinant of j comes in the denominator. So, if you look at this relationship, if this one becomes equal to 0, then your theta dot will become equal to infinity. Okay. So, becoming infinity, what does it mean in the physical world? So, in terms of the physical robot, what it means is that if you want to give infinite velocity, you need infinite energy. Now, you know that motors cannot give infinite energy, cannot produce infinite torque, okay? And hence no motor will be able to produce an infinite velocity. Now, not only that, a motor will be always able to produce a finite amount of torque, which means that after that torque it will not be able to produce any more torque. So, it will not be able to increase the velocity beyond that. Okay. And this relationship basically tells us that it is not possible to go to for the joint velocity to go to infinity. It is not even possible for the motor to exceed the maximum motor torque. Okay. So, this point where the determinant of j becomes equal to 0 is what we are called singular points. So, determinant of j equal to 0 are called singular points. Okay. Now, something to remember in terms of the physical robot, as I just said, that motor cannot obviously give infinite velocity. Okay. It can give only finite. So, it is not possible to go to a singular point. It will not even be possible to go near a singular point. Okay. So, depending on what is the maximum motor torque, it will go somewhere near a singular position and then it will stop there. It can't go beyond there. Now, let us see for a 2-link manipulator, for this manipulator itself, let us see what are the singular points or singular positions. Now, we said that the Jacobian is equal to 0 at a singularity. So, in this particular case, this is my Jacobian, right. So, where is this Jacobian, the determinant of this Jacobian equal to 0. So, let us write it again and say the determinant of j. So, determinant of j is equal to the determinant of minus L1 sin 1 minus L1 sin 1 2 minus L2 sin 1 2, and here it is L1 cos 1 plus L2 cos 1 2 plus L2 cos 1 2 here. Okay. So, I want to find the determinant of this now, the same as the previous one. So, this is the same matrix that I wrote here. I am just writing it here again. Okay. Now, I want the determinant of this. Now, how do we find the determinant of j? Basically, I multiply this into that minus that into that. That is how I find the determinant. Now, it looks like there are a lot of sine and cos terms, but what happens is, because there is sine and cos terms, when you multiply it like this, what happens, a lot of the sine and cos will cancel each other out. Okay. And what we are left with is a very simple term L1 L2 sin 2. So, it is interesting to note that theta 1 does not appear in this expression. So, theta 1 does not appear in this expression, and only theta 2 appears, and L1 L2 are the link lengths. Okay. So, determinant of j is equal to L1 into L2 into sin 2, and in case of singularity, this is equal to 0. Now, you know that L1 L2 are physical lengths, so they cannot be equal to 0. So, L1 and L2 cannot be equal to 0 because they are lengths, they are link lengths. Okay. So, they cannot be 0. So, the only possibility is that sin theta 2 is equal to 0, and this is for condition of theta 2 equal to 0 and 180 degrees. Okay. So, as I had said earlier, that sine and cos always have 2 terms. So, theta 2 will become equal to sin theta 2 will be 0 for values of theta 2 equal to for values of theta equal to 0 and 180 degrees. So, these are the 2 positions where the manipulator becomes singular. Now, if I were to draw it, what would it look like? So, this is my 2-link arm. So, theta 2 equal to 0 would mean that it is completely stretched like this. Okay. So, it is completely stretched. So, my theta 2 is 0 degrees here, theta 2 is 0, is one position, and theta 2 is equal to 180 is the other position, which means it is completely folded like this. So, it is somewhere here. So, one point is here. So, that is this is one of my singular points. So, one of the singular points is here and the other one is there. Now, when it is moving, something to note here is that it does not depend on theta 1. So, theta 1 has no effect on this. So, basically I can have any theta 1, which means this can rotate like this and come up to 360 degrees. So, what we do get is a circle like this and a circle or a point in there, depending on the two link lengths L1, L2. So, basically all these points are basically called boundary singularities, and there would be one point there or a small region depending on the ratios of L1 and L2. Okay. So, if L1 and L2 is 1, then this will be a point here. If L2 is greater than L1, then there is going to be a region in this region, which is also singular. Okay. So, what we have seen here is that singularity is only happens on at two locations where theta 2 is equal to 0 and 180, and these are called boundary singularities. So, at a boundary singularity, the manipulator, it is like the manipulator is locked in that position, and you will not be able to give any velocity in this direction. Okay. So, this is what it means. Essentially, in this position, it cannot obviously go in this direction, it is out of the work volume, but you cannot give a velocity in this direction. And what will happen is, if the manipulator tries to move in this direction, or when it comes with a velocity in this direction, okay, it will become so the two directions I am talking about, one is this direction and the other is that direction. If I want to give a velocity in these directions, that means if I want to give some x dot, which is going to bring it to this position, very close to theta 2 is equal to 180 degrees or 360 degrees or 180 degrees. So, let me put it here. So, theta 2 equal to very close to 0, what will happen? Your velocity at the joint will start going towards infinity, will become very large. Infinity here basically means very large velocity. Okay. So, this are called boundary singularities, and we will see that physically when I am trying to move in this direction, and when the joint comes very near to here, the joint velocity will become very large. Now, if you see the reverse question, is, this is telling me that when we are going to, when determinant of j becomes equal to 0, then your theta goes towards infinity, which means it takes the energy required to drive the system becomes very large. Energy goes towards infinity also. This is what it means. Now, this could be a way of trying to minimize energy. So, if you look at this, going back looking at this expression again. So, here I am saying that if determinant becomes equal to 0, then theta goes towards infinity, okay, which means the joint velocities are going to infinity, energy required is going to infinity. But if I see the reverse of this question and I say that under what condition would the joint energy requirement become minimum, then again we can come back and here say, if this becomes maximum, then the joint velocity will become minimum, okay, or the joint energy requirement will become minimum. So, this expression, which is very simple, but is very important, because it tells us two things: one condition where the joint velocity will become maximum, the other condition where the joint velocity will become minimum. So, now if I want to say that I want to let us look at it like this, where when we want to perform a task, when a robot performs a task, okay, a robot is going to perform a task in space. Now, we know that the work volume, it has to be inside the work volume, that is fine. So, what is the work volume? The work volume is something like this, okay, this is a point. So, everything inside here is the work volume, okay, or the work area in this case. So, where should it perform a task? Say, for example, if you are looking at the example of picking and placing an object, I am picking up an object from here and I am placing it somewhere, or I am assembling a part like a pen, where I am assembling this cap onto the pen. So, this task is inside my work volume, and my work volume is very large. So, I can do the task here, I can do the task here, I can do the task here, it is inside the work volume. Similarly, I can do the task here, I can do the task here. Okay. So, where in this work volume should we perform the task? Now, how do we answer that question? So, the question is, where in work volume should the task be performed? Should the task means any task be performed. Okay. The first condition is that it should be inside the work area, which is fine, right. So, it should be inside the work area, which is quite logical that it should be inside the work area, but inside the work area we have such a big area. Where inside? Now, the second way of answering it could be, the second condition would be the energy requirement the energy requirement to do the task, the energy requirement should be minimum. Okay. So, we are going to perform a task such that the task required to perform that energy will be minimum. Now, how do we answer that? Or how do we find the area? Again, we go back here and we see that if this fellow becomes maximum, if this determinant j becomes maximum, then the energy automatically becomes minimum, because this is maximum means this gets minimized and your joint velocities will get minimum. So, again we say that the determinant of j should be maximum, okay, for minimum velocities, for getting the minimum joint velocities, okay, minimum velocity at joints, which is indirectly equal to minimum energy. Okay. So, we are trying to answer the second question, that where the task should be performed, by saying that we should perform the task such that, or in an area where the joint velocities are going to become minimum, and because of which the energy will become minimum. And we see the determinant of j, we just saw the determinant of j is L1 L2 sin 2. Again L1 L2 are constants, these two are constants because they are link lengths. So, sin 2 is maximum, and we know that the value of sin 2 to be maximum has to be equal to 1. Okay. Sin theta 2 should be 1, which implies that theta 2 should be equal to 90 degrees or 270 degrees. Okay. So, this tells us the gives us the answer that you should perform a task such that your joint theta 2 should be having an angle of 90 degrees or 270 degrees. Now, what are these two angles in terms of this manipulator? One is, it is this configuration. So, this would be one position where theta 2 is 90, the other is downward here where this one is, this is 90 here. Okay. So, this is theta 2 equal to 90 and this is equal to 270. So, we should perform a task in a location where your theta 2 is 90 or 270 to get minimum energy requirement. Now, does it really happen like that? Now, if you look at all the tasks that robots perform, they will normally be performing in this region, either this side or this side, okay, but it will be in this region, and in this region your angle here is more or less 90 degrees. Okay. This indicates that this is the area where the energy requirement for doing a task is minimum. Now, it is interesting to note that is it also applicable to human beings? Okay. Say for example, when we are performing a task, the example I just gave, I am going to pick up an object and keep it somewhere, okay, and or I am writing with the pen, you are writing with the pen, okay, on the board, or we are assembling a task. An assembly of a task is like I am trying to put the cap onto the pen. Where in the workspace are we performing? So, if you notice very carefully that when I am writing, essentially my angle here is theta 2. So, this is my theta 1 and this is my theta 2. So, if I see my link, this is L1, that is L2. So, this is my theta 1 angle, this is my theta 2 angle. So, when I am writing, essentially we write like this, and the joint angle between this and this is 90 degrees, which indicates that we are also minimizing energy. And essentially whenever we are performing a task like this, or I am picking up and keeping something, you will find that this tends to go towards 90. Okay. And this is verifying that whatever we just proved here, that theta 2 should be around 90 degrees or 270 degrees for getting minimum energy. So, we have evolved, and in the process of our evolution, it has been ensured that essentially we perform tasks by minimizing energy. Now, interesting here again is that theta 1 has no effect. So, this only depends on theta 2, it does not depend on theta 1. Okay. So, we can perform the task anywhere here, okay, in these configurations where theta 2. So, this full region is the region where basically we are going to perform tasks. And if you look at any industrial robot, or you look at a robot where it is doing pick and place, you will always find that it is somewhere or it performs the task such that the joints theta 2 tends to come towards somewhere near 90 degrees. So, this answers two important questions: singularity, where you should not go, and which is very clear from here, wherever determinant tends to go towards 0, your joint velocities will tend to become very high. The second is where in the workspace should you perform a task, and this is also answered from here, that it should be such that your joint angles theta is in this range, and so which means this area. For humans also, it is interesting to note that we also satisfy this condition. So, let us look at a very simple example which will give us an idea of how this singularity is actually works, or what is the effect of it. So, let us look at this example. So, we have a two-link manipulator again. So, this is an example or a problem. Let us look at an example, a very simple example of a two-link manipulator which is going to move. So, let us again take the example. This is my arm, it is one link here, one link here, and I want to move from here to here in a straight line. Okay. So, essentially this is a point B and this is a straight line A. My arm is like this, if you can imagine, this is L1, this is L2, and I want to move like this. So, if I want to move the end effector with a velocity of 1 meter per second, then what is the corresponding joint velocities we want to find? So, if I simply draw it here, so this is the problem that we are trying to solve. So, this is my x axis, y axis as before. We have a manipulator. So, this is a manipulator link, one link here and another link there, and this is my end effector. Okay. So, this is my manipulator, this is my end effector, this is my joint angle theta 1, this is my joint angle theta 2. So, this way is theta 2. So, counterclockwise we are taking as positive. The link lengths are L1 and L2. Okay. Now, I want to move this manipulator with a velocity in this direction, which is given by x is equal to 1 meter per second, okay, and y is equal to 0. It is moving in a straight line along x, so it has no y component, and I want to find what is the corresponding velocity theta 1 dot and theta 2 dot. Okay. So, this is my question. I want to move the end effector in this direction from points, let us say from point B to A. This is my point B, this is my point A, and I want to move it in this direction with a velocity of 1 meter per second. So, what should be the corresponding joint velocities? How do I proceed to solve? Essentially, we write down our Jacobian again. So, our Jacobian matrix that we found out was, so let me write it this way. So, okay, let me write it here, x dot is equal to j into theta dot. So, if I want to find what is theta dot, then I need the inverse of x dot of j, which is equal to adjoint of j by the determinant of j into my x dot, right. So, this is what we need, and we are given that x dot is equal to x is equal to 1 meter per second and y is equal to 0. Okay. That is my velocities. Okay. So, how do we proceed? So, basically what we need to do is to find j, and we have just seen that j is equal to minus of L1 sin 1 minus L2 sin 1 2 and minus L1 sin 1 2. This is equal to L1 cos 1 minus plus L2 cos 1 2, and here it is L2 cos 1 2. That is my Jacobian matrix. Okay. So, now what we need to do is we need to find the determinant of j. So, we know that we just saw that the determinant of j is equal to L1 L2 sin 2. Okay. This we have just seen. Now, next what we need to find is we need to find the adjoint matrix of j, and what we do is let me write it. So, theta 1 dot, so theta 1 dot and theta 2 dot is equal to the determinant of j, which is 1 by L1 L2 sin 2 into the adjoint of this matrix. So, what is the adjoint of this matrix? So, first term, that is going to be the first term here is going to be, so we are going to take the first term, which is L1 L2, okay, cos 2. So, L2 cos 1 2 is the first term, you know how to get it. So, for the first term we said that is not considered, only this term is considered, and we bring it there. So, L2 cos 1 2, the second term here is L2 sin 1 2, and then it is minus L1 cos 1 minus L2 cos 1 2 and minus L1 sin 1 minus L2 sin 1 2. Okay. So, we get our two terms. So, we have got our adjoint matrix, which is given by this matrix, and on my other side, if I write in matrix form again, this is my x dot and y dot. So, here it is x dot and here it is y dot. Okay. Now, what are we given? We are given that x dot is equal to 1 meter per second and y dot is equal to 0. So, if I want to find for the first one, theta 1 dot is equal to 1 by L 1 L 2 sin 2 into this into x dot. So, what is that equal to? L 2 cos 1 2 into x dot, right. So, this is what we get. So, when we get that, we see that L 2 and L 2 will cancel. So, what we will be getting is 1 by L 1 sin 2 cos 1 2 into x dot. So, that is my first velocity of the joint, which we are getting as cos of 1 2 L 2, and let me write it this way. So, let me write it here by L 1 sin 2. Okay. So, this is giving me my first joint velocity. Now, the second joint velocity theta 2 dot is this this into that. Now, we know that y dot is equal to 0. This is x dot is equal to 1 meter per second, that is given in the question. Y dot is equal to 0. Okay. So, basically when we are multiplying this into that, what will be getting? Theta 2 is equal to L 1 minus of L 1 minus L 1 divided by L 1 L 2 sin 2 into cos 1 here, and the second term is minus L 2 L 1 L 2 sin 2 into cos 1 2. Okay. So, here what we can see is this will cancel, L 1 will cancel, L 2 will cancel, and what we will be left with is minus C 1 minus of C 1 L 2 sin 2 minus of C 1 2 L 1 sin 2. Okay. Y is equal to 0. So, I did not take the second term because it is going to be 0. Okay. Now, so this into x dot, right, that is going to be my velocity. Now, let us look at an example. Let us look at put in some numerical values and see. So, this is my first velocity theta 1 dot, this is theta 2 dot. Now, for different values of theta 1 and theta 2, let us see what it comes out to be, what the velocities come out to be. So, let us assume that the manipulator is moving from here. So, let me make the assumption that the manipulator is first like this. Okay, it is completely stretched, it is here, then it has moved to the red position, then it has moved a little bit more below and it has come till here. So, it has moved a little bit more and it has come till here, okay, and it has moved a little bit more and it has become almost straight. Okay. So, let us make the assumption that this is end effector is moving in a straight line like this. So, first it is here, then it comes here, then it becomes straighter and straighter as theta 2 is closing and becoming close to 0, the end effector is coming towards the point A. So, towards the point A, let us make the assumption that the two values of let us say that theta 2 is equal to 358 degrees, which is very close. So, this one is this angle here is 358 degrees, and theta 1 is 1 degree, theta 1 is here. So, theta 1 is 1 degree. Okay. Let us make the assumption that theta 2 is 358 and theta 1 is 1 degree. So, what we need to do is simply take the values of theta 1 and theta 2 and put it in this expression. First expression is here, second expression is there, and we will get the corresponding values of the joint velocities. So, if you do that, what we do find is theta 1 comes out to be equal, theta 1 dot comes out to be 95 radians per second, and theta 2 comes out to be 191 radians per second. Okay. So, as what this means is that as the end effector is going towards the point A, what is happening is the velocity of joint 2 is increasing rapidly, and if you convert it into degrees, it becomes very large velocities like 11,000 degrees per second, which is a very large. So, this is still not singular because singularity would happen when theta 2 is equal to 0, okay, or 360, but this is very near singularity. So, this is what I meant by it cannot go to singularity, it can go as it goes very near a singular position. This joint velocity will start, theta 2 will start becoming very large. Okay. So, it basically means that if you are trying to control the velocity in this direction or in this direction, that is the x direction, extremely large, and you will require very large amount of energy. Now, in the case of the human also, if you look at our hands, then also we have the same issue. Now, when we look at our arm, which is fully stretched like this, that is my theta 2 is very close to 360 degrees or 0 degrees, then what you find is you cannot move in this direction. So, what I mean is I cannot move in the x direction, this is my x direction. So, I cannot have a velocity in this direction because we are near a singular, we are in singular position now. Okay, this is the boundary singularity, and this shows that if I want to move in a straight line as I am going near there, it will be very difficult to control velocity in this direction. I can move in this direction very easily, but in this direction it will start becoming very, very difficult. Or it is one way of saying that the matrix is going to lose rank once you come very near a singular position. So this gives us an example of a two-link manipulator and the importance of the Jacobian matrix, and how the Jacobian matrix can be used to determine singular positions, and also the relationship between the joint velocities and the end effector velocities. Now this is a physical system, right. So if the velocities are related in some way, joint velocity and end effector velocities, then the forces, torques would also be related, right. So if the end effector, we are applying a force here. What I mean by this is we have a manipulator like this and some force is being applied there. Okay. Let us call this some force in the fx and y direction. Now what will happen is this force here, because this is a rigid link, will get transmitted onto this link here, will be transmitted to this joint here. Now once this force is transmitted here, okay, it will again get transmitted onto the base joint here. So this force is moving like this from here to here, that is the direction in which it is moving. Now if there is a force here, a force is acting here, let us call it F3, then this, to have the force here, we will need a resultant torque at the joint. That means just to keep the force, just to balance this force, we need a resultant torque at the joint here, and to balance the force here we need a torque at this joint here, and these forces are moving from the tip downward. So the example that I can give is if a robot is applying a force on a wall, for example, suppose I am pushing against the wall with a particular force, then this force is getting transmitted backwards. So I am pushing against the wall with some force F, this force is from here, it is coming here, then from here it is coming here, and each one to balance those forces I will need to have a joint torque. Now this is also related by the Jacobian. Now let us see how that is related by the Jacobian by looking at this very simple formulation of the force transmission. Now let me draw a very general diagram here. So this is a link. Now it can be in 3-dimensional space, so it can have any shape. Okay, so this link is shaped like this, and the bottom there is one more link here. Okay, this is one link, and this is connected to another link here, which in turn is connected to another link. Okay, so if you can see this this figure that I have drawn. So the force, the first thing that we do is we put our axis, right. So let us put our axis. So this is my Z1 axis, this is my Z2 axis. So this is my Z2 axis, okay, this is Zi plus 1, let us call it Zi and Zi plus 1. Now this is my Z axis pointing in that direction and pointing in this direction. Let us say my x axis is in this direction, so this is xi, and the next x is in that direction, xi minus 1, xi plus 1. And there is a distance between this axis and that axis, let us say, which is equal to pi and pi plus 1. So the frame I is of the previous link, and the frame I plus 1 is of the next link, if you can imagine. So this is my frame which is fitted onto the next link, and this is the frame onto the previous link. So we just number this as I and I plus 1. Now let us say that there is a force and moment acting. So at this origin here there is a force Fi. Fii is the force which is acting here. Okay, so there is a force Fi acting here. Okay, Fi, and there is a moment Ni. So force Fi and a moment Ni which is acting at the origin of the frame here. Now on the next frame there is going to be a force and a moment again. Okay, so let us call this Fi plus 1 and Ni plus 1. So this is the force and moment acting there. Now what we are interested in is saying that if there is a force and moment acting on this link, this force and moment will get transmitted backwards, and to support this force and moment will require a torque at this joint, right. So the force and moment, something that I just drew some time back, is if there is a force and moment acting here, to balance this I will have to produce a moment here, a torque here. Now this fellow will get reflected onto this joint, so it will have some component here now. Now to balance this I will need a torque here. Okay, so if I call this F2, I can call this F1, and we see that the forces and moments are moving in this direction. From the top they are coming backwards, and finally they are coming to the joint 1. So, what we are trying to find is if there is a force and moment acting on the I plus 1th link, how does it get transmitted onto the Fi link and then Fi minus 1 in that direction up to the 0 link. And that, to keep those in position, we are going to read what are the corresponding joint torques that are required. Okay, so, that is what we are trying to find out. Now, looking at this relationship, looking at the figure that I just drew, we are seeing that this force will get transmitted, okay, in either direction. So, this force Fi plus 1, which is acting here, will get transmitted to the previous axis, to the I axis, but we also see that there is a distance between the origins of between the axis, the z axis of this I plus 1 frame and of the ith frame, and that is my I plus 1. So, there is a distance between this axis. Okay. So, the moments are going to get transmitted and the force will also get transmitted, but this force here will also cause a moment about this axis now. Why? Because there is a force Fi here. So, the force into the distance will cause a moment here now. So, forces and moments are going to move, and a moment will be created also, because the force is acting here and this force into the distance will be a moment about this point. So, what are the forces balance equations? Now, we are considering static condition. So, for static equilibrium, so for condition of static equilibrium, we know that the forces and moments in the 3 directions should be equal to 0. So, sigma Fx is equal to 0 and sigma m is equal to 0. So, Fx, Fy, Fz must be equal to 0 and Mx, My, Mz must be equal to 0. So, forces and moments must be equal to 0. So, first we use this equation, then we use this equation, and then we see that how the forces move from frame to frame. Okay. So, now let us write our first equation. So, Fi in frame I is equal to, so this Fi in the Fxy direction will be equal to the force acting on the next frame. So, the force acting here must be equal to the force acting there. So, force is equal to Fi into I plus 1. Okay. And what about the moment? Now, the moment is Ni must, that is my moment I plus 1 plus F plus the moment caused, because there is a distance between Fi Pi into Pi plus 1 cross Fi plus 1. Okay. So, first is this force is equal to that force. Second is this moment is equal to that moment plus a moment being generated about this axis by this force. So, this force into this distance will give us a moment about this, which is the second one here. Okay. Now, if you see that the frames are different. So, the I plus 1 and the ith frame are different frames. So, in order to make everything with reference to frame I, what we do is we are going to multiply with the rotation matrix. So, we have the rotation matrix that relates the 2 frames. So, it is frame I to I plus 1. This relates the frame I plus 1th frame to the ith frame, right. So, this is the direction in which it is going. So, I plus 1th to the ith. So, I am going to multiply equation 1, this is my equation 1, and equation 2 by this rotation matrix, and which is going to give me the 2 equations in frame I. Okay. So, if I do that, what do we get? It is f of I plus 1 is equal to r I into I plus 1, and this f now the next fellow gets converted into the ith frame, okay, I plus 1. So, this one was Fi, now you see it has become I plus 1, which means that it has come to frame I. Okay. So, I am multiplying it with the rotation matrix. So, from equation 1 we get this equation which relates the forces, we can call it equation 3, and if I do the same with this equation, then what do we get is we get Ni I plus Ni is equal to rotation matrix I into I plus 1 into I plus 1 into I plus 1 plus. Now, note that if I put my rotation matrix here, I multiply this by R I into I plus 1, then it becomes I f of I plus 1 right, which is actually this term. Okay. So, this is my term now right on top here. So, this term is equal to this term. So, if I put in this equation, when I multiply with the R matrix, this will become R into this, which is equal to this. So, what I do is I simply put P I plus 1 cross F I now from this equation. So, if you understand what I have done is I have multiplied equation number 2 by R I to I plus 1. So, in this point here, it is going to become this term. Now, this term is equal to this term, if you can see. So, actually it should have been this into R into F I, but R into F I is equal to F I. So, it becomes equal to P cross F I. Okay. So, that is how we have got our equation number 4. So, there are fundamentally two equations. The two equations are, one is this equation, which gives the relationship between the forces from one frame onto the next frame, and this is the equation that gives with respect to. So, this gives the force equations, this gives us the moment equations n. So, using these two equations, we can move from frame to frame. So, any force which is acting on one frame, we can convert it to the next frame. Now, let us see how we can do that. Let us again look at a very simple example before we proceed to clarify how it works. Is essentially we have a 2-link manipulator here, and this 2-link manipulator, this is one link, this is another link, okay. And there is a force and moment acting. So, let us say that there is a force and moment acting on this link. So, F3 is acting here, there is a force F3 acting, and F3, the force acting on the third link, is equal to Fx, Fy and 0. There is no moment acting, let us say, and this is completely 0 0 0. Okay. So, the first thing what we need to do is to put our frames. So, let us put my Z0 Z1 here as per DH notations, x1 is here, x0 is here, and x1 is along here. Similarly, Z2 is here, and this is my x2. Okay. Now, what about y? So, the y3 is here, this is my that is 2, this is my and my third frame here, Z3 is here, x3 is there, and y3 is there. Okay. So, we have assigned our axis. The z axis is the axis of rotation. You should be able to figure this out now, that this is basically a rotation which about this joint, right. This is a rotation about this joint, and this is the end effector. Now, at the end effector, we have a force F3 acting. Okay. Now, I have assigned my frames, x2 is here, x3 is here, and let us talk about the link lengths also. Let us say this is my link length L1, this is my link length L2. Okay. Now, the force and moment acting on the third joint is given by F3 and N3, which is given by Fx, Fy. What is the meaning of Fx? What is the meaning of Fy? It means Fx is acting in this direction, Fy and Fy is acting along the y axis of the third frame. So, that is the meaning of F3. Okay. Now, there is no moment there, and hence this is equal to 0. Now, what I want to find is, in order to resist this force F3, what is the torque required tau 2 here, and what is the torque required tau 1 here? That is what I want to find out. And how do we proceed? We essentially use these two equations. The first equation is for giving us the relation between the force between I plus 1 frame to that of the ith frame, and in the second case is giving us the relation between the I plus 1th frame to the ith frame. So, we simply need to put in these two formulas, and we are going to proceed. What is the rotation matrix? The rotation matrix is a rotation about the z. So, my rotation matrix is going to become cos minus sin, sin cos 0 0 1 0 0, and it will be 1 2 or 3 depending on which is the frame we are talking about. Okay. So, now this is a rotation z about my theta axis. So, F3 is given by this. What about F2? Now, F2 is the force acting on the second axis. Where is the second axis? The second axis is somewhere here. Second axis is on that joint. Okay. So, if you see the second axis, it does not have any rotation with respect to the third axis. So, the z's are parallel, the x2 and the x3 are the same axis, okay, and y3 and y2 are also parallel. So, there is no effective rotation between these two matrices, and hence F2 is equal to F3 now. F2 is equal to F3, which is equal to Fx, Fy and 0. Okay. Please note that why these two are equal, essentially because, so let me write it this way. is equal to f x, f y and 0. Why? Because there is no rotation between. So, there is no rotation between 2 and 3 axis. So, please note that. Now, what about N 2? So, from the third frame we have come to the second frame in terms of force. Now, let us look at in terms of moments. What about N 2? N 2 is equal to the moment acting on the axis at joint 2. There is no moment on the third frame. Okay. So, essentially if we go back here, there is no moment acting on the third frame. So, this will become 0. So, the only moment that will come is because of this term now. So, because there is a distance L and because there is a force acting at the frame origin 3. Okay. So, if I look at this expression now, it will only be because of the force act because of the L 2 x 2 cross f 2 f x f y 0, right. So, this is what we are getting in terms of our. So, if you just go back here and see again, it is essentially the distance. Now, the distance is L 2 and the force F I is F 2, which is acting on 2. So, essentially it is this into F 2 force L 2 cross F 2, okay, which is equal to L 2. So, L 2 is this distance, it is along the x axis. So, that is why I am writing it is along the x axis cross F 2, which is f x, f y and 0. Okay. Now, how do we find this out? We essentially find this out. How do you find this term? It is basically finding the cross product. So, it is I, j and k, and this is equal to L 2 0 0, this is f x, f y and 0. Okay. So, when you find the cross product like this, we get N 2 is equal to 0 0 L 2 f y. Now, when we come back and see here, the force which is the f x force along the x axis will not cause a moment about this point. It cannot, because it is along the x axis. The only moment will be with the force f y, which is along y into the distance L 2, and that is what we are getting, L 2 into f y. Okay. So, we are getting the force at axis 2 and we are getting the moment at axis 2. Next, from here let us move on to axis 1 using this formula again. So, I becomes equal to 2 and I becomes equal to 1, and we get for forces and moments, what do we get? So, f I f 1 is equal to, now there is a rotation matrix which is C 2 minus S 2 C 2 0 0 1 0 0. Okay. So, this is my rotation matrix into the force f x f y 0, and if you open it out, what we get is C 2 f x minus S 2 f y, and this is S 2 y plus C 2, sorry, this is f x f y f x, and this is f y, and that is 0. Okay. So, we get these two terms like this, and what about the moments? Now, moment 1 is equal to 0 0, the moment on the previous, it is L 2 f y plus what we get is L 1 in the direction of x cross f y, right. And if you put in the values, you just need to put in the values of this one here, find the cross product, what we get is 0 0 0 0 L 1 S 2 f x plus L 1 C 2 f y plus L 2 f y. Okay. So, this is what we get as the moment on the first axis. Okay. Now, this is the moment on the first on the second axis. Now, moment means torque, this is about the z axis. Okay. So, there is about the z axis. Okay. Similarly, this is the moment about the z axis of the first axis. Now, if I combine this this term and this term, these are the two moments which are acting, and if I combine it, then I am going to get my torque 1, which is equal to L 1 S 2 into f x plus L 1 C 2 plus L 2 into f y. This is my torque 1, and torque 2 is equal to L 2 f y. Now, if I write this in matrix form, okay, if I write the same expression in matrix form, then tau 1 tau 2 is equal to, so in matrix form this would be equal to L 1 S 2 on one side, then L 1 C 2 plus L 2, and here it is 0 here it is L2, and here it is going to be Fx, Fy. Okay. Now, this is also called the Jacobian. Now, this Jacobian relates the end effector forces to the joint torques, and this is expressed in frame 3. So, basically what we are trying to see here is that the relationship between the end effector force is also given by and the joint torques is given by this relation tau is equal to J transpose into the end effector force, which is F. Now, something to note here which is very important is that in this particular example the forces were expressed in the third frame. Okay. The forces are expressed on the third frame, and hence the Jacobian is also that we found is also in the third frame. Okay. This is not the Jacobian that we got some time back, but you can convert the Jacobian convert this fellow, the third frame fellow, multiply by the rotation matrix, and you can convert it into the first frame Jacobian also. They are equivalent, okay, but they are not the same. So, this is also called the Jacobian, and we see that the Jacobian also relates the end effector forces to the joint torques, and so this can also be derived in another way. So, if you look at a single link here, so from principle of virtual work. So, if you can talk about virtual work here. So, if there is a force acting Fx here, this will cause a very small deflection, say dx, and correspondingly on this side there will be a very small torque, let us call it tau, which is going to cause a deflection of d theta. Okay. So, a small force causes a small deflection, a small torque causes a small angle change here, and this both have to be equivalent. So, F into x, so F into dx, F transpose into dx must be equal to tau or transpose into d theta. They must be equivalent from virtual work. Now, we know dx is equal to F transpose dx is equal to j into d theta. Okay. So, this is tau into d theta. So, we get this relationship, this relation dx, we just saw it some time back, is equal to j into d theta. So, d theta will cancel. So, we will have F transpose into j is equal to tau transpose. If I take transpose of both the sides, we get we get tau is equal to j transpose F. So, this relationship also can be obtained from here, that the end effector force is related to the joint torques by the Jacobian. So, again something to remember, this is at the nth joint or the last joint, this is not the first joint, and hence the Jacobians are different, but they can be converted to one another. So, today we end the lecture here, and we will continue in the next class. Thank you.